end of the marine biomes lecture where my phone cut off last week, and also the freshwater biomes lectures. This will cover both of those. So I believe we finished this, or most of this PowerPoint. We talked about kelp forests and coral reefs and how they are the most biodiverse reefs and how they occur in tropical areas between the two tropics. Warm temperatures, shallow enough to allow light penetration because algae that live with the corals are the primary producers in coral reefs. I believe we are on to the next slide, which talks about a few other coastal biomes that we see. First one is the intertidal zone, which we talked about a bit in the previous lecture. The space between high and low tide is exposed to widely varying physical conditions. And so life in the intertidal zone must be adapted to be exposed to open air, to intense sunlight, to crashing waves, and to be submerged underwater for certain periods of time. We're not going to talk about the mechanisms that cause the tides, but they are caused quite simply by the gravitational pull of the moon and the sun to a degree as well, but we're not going to talk too much about that. Organisms here are adapted, like we said, to a wide variety of conditions. Estuaries, these occur where rivers empty into the ocean. The next and last slide for this marine biomes part is going to show you what happens when fresh water coming from a river meets with salty water of the ocean. Estuaries occur where rivers empty into the ocean. The term for water that does not have the 35, roughly, parts per thousand salinity of ocean water, or the 0, roughly, parts per thousand water of fresh water is called brackish water. So this is water that is not truly fresh water, but it's not oceanic salt water either. And so when the waters mix, you get brackish water, and that occurs in estuaries. If you were to take the Mississippi River all the way down to Louisiana, where the Mississippi River empties into the Gulf of Mexico, that would be an example of an estuary. Salt marshes are another marine biome, a coastal biome. These occur in very shallow expanses in temperate areas. If you were to go along the northeast coast, if you were to go along the Gulf Coast, you would find massive expanses of salt marsh grasses. Lots of primary production happening, not a lot of plant diversity here. It's mostly just a few species, but there are a lot of individuals of those few species. Key with these guys is they're found in very shallow waters because the plants themselves are rooted to the submerged ground, but they still are emergent above the water. So salt marshes, very shallow, much more shallow, for instance, than the kelp forests. And then there's mangroves, which exist in shallow areas in tropical regions. Mangroves feature emergent trees, and so usually the root system of these trees provides a lot of nooks and crannies for several fish species. In the U.S., the only place you can find mangrove forests is in the Florida Keys and that general area. Yeah. So these are some coastal marine biomes. Speaking of estuaries, a little bit more on them. So this is an incoming river, fresh water, salt water here. You can see you have it coming in, there's some upwelling, it comes back around. It does not mix immediately with the fresh water. Fresh water is less dense than salt water, and so it floats above salt water when they meet. And you can see here that it forms a separate layer above the salt water for quite a while, long after it's actually emptied out into the ocean. And so the diluting of fresh water into the 35 parts per thousand salinity of the ocean is quite gradual. And there's quite a bit of brackish water even a ways out from the actual river mouth itself. So that's what occurs in estuaries. Onward to freshwater. This is going to be a relatively short topic. What does it mean to be fresh water? Does it mean there's literally zero salt? Not necessarily. Fresh water means that there is less than 0.5 parts per thousand salinity, compared to 35 parts per thousand in the ocean. Some landlocked lakes, like the Great Salt Lake, for instance, or the Dead Sea, another example, they're also saltwater, even though they're not marine or oceanic. And so just because water is inland or landlocked does not mean that it is freshwater. But a freshwater environment, salinity of less than 0.5 parts per thousand. Many different habitats include fresh water: marshes, streams, rivers, lakes, pools, bogs, fens, swamps. There's a whole host of them. We are not going to get into the specifics of too many of these. I want to focus on some of the freshwater environments that we see here in Missouri, but we'll revisit some of the other wetland types perhaps a bit later in the semester. If we're looking at the actual volume of fresh water on the earth, it's not that much. Remember, 97% of the volume of water on earth is saltwater in the ocean, and 2% is locked up as ice at the pole, which means less than 1% is actually flowing fresh water, or not necessarily flowing, but liquid fresh water. If you're curious, that's Crater Lake in Oregon. It's a pretty beautiful sight to see. And a huge chunk of the fresh water that we have exists in a couple of large, deep lakes. The Great Lakes are quite a bit of the volume of the Earth's fresh water, for instance. But it's not that much compared to the total, less than 1%. So let's talk about some of the freshwater environments that occur in Missouri. Rivers, I'm sure you're all familiar with. What is a river? Technically, a collecting channel that drains the world's landscapes. That's it. Ultimately, rivers flow out to the ocean, and so rivers are always flowing downhill. One thing to note, surrounding a river, there is a zone of land called the riparian zone. So if you've got a river meandering its way across a landscape, there's going to be a zone of land around the river, and that zone of land is called the riparian zone. So the actual water of the river, if I color it in, it'll make the illustration stand out a bit more. So the water of the river seeps through the soil, providing moisture availability to the surrounding land that does not exist, for instance, out here away from the river channel. And so different plant species can grow right beside the river because they have different water requirements, and the river being there and the water seeping out through the soil helps those plants to meet that requirement of water. It's easy to observe in deserts compared to around here. There's enough moisture that trees can grow away from rivers here. But in deserts, you have a lot of species that can only grow where there is that riparian zone. And so here is, I believe this is the Colorado River, I'm not sure. It is a river in the desert. And it's hard to see with the lighting the way it is, but right here is the edge of the riparian zone. And so you've got cottonwoods and willows and other species that can't grow even out here. But they can grow right along the river because the water seeps into the soil along the riverbank and provides enough moisture for them to grow. And so that is what the riparian zone is. Another term to be aware of is benthic. Benthic simply means the bottom substrate of a river, right? What's the difference between a stream and a river? Ultimately, it's really just how big is it. Streams are small, rivers are larger. That's the general idea. Creek and stream are pretty interchangeable. Here's a picture with some numbers associated with a system of streams and what looks like ultimately a river. What is this showing? Well, it's showing us a concept called stream ordering, or stream order. And so, look at the number 1 up there. Number 1 is on what's called a first order stream. Alright, these are the headwater streams. This is where ultimately the channel originates, and several of these first order streams will empty ultimately into what's called the second order stream. Characteristics of first order streams, again, they're quite small. They tend to be much cooler in temperature. There might be a spring at the origin of some of these first order streams, right? Because they're cooler, they tend to have higher amounts of oxygen, which we'll talk about in a little bit. But ultimately, first order streams will meet and empty into a second order stream, which tends to be larger, wider, deeper than a first order stream. Second order streams together will empty into a third order stream. By the time we get there, we're probably using the designation of river. This could be smaller rivers. I believe the Burbus River runs close to Union. That could be considered a third order stream. The Merrimack River would be somewhere either 3 or 4, third or fourth level stream, fourth order stream. Large, deep rivers with a slow current, think Mississippi, Missouri River. First order stream, think you're out hiking in the Ozarks and you find a cool stream that you can cross with a lot of rocks you can jump across. You might get your feet wet, but it's not very deep. So, very different environments. And the way that it's often designated is first order, second order, third order, etc. So just be aware of how that system works. Alright, a word to know is biota. Bio is a word that means life. So biota means what life is present in a particular area. And so for rivers and streams, when we're talking about the life that is in them, it really depends on the conditions of that particular river or stream. What are some things that influence the biota? I got 4 major ones here listed for you. The amount of light that's available, which can depend on a number of things. It can depend on the turbidity of the water, how clear is the water, the depth, if it's quite deep. Some of the deeper regions might not get much light availability for plant growth. Temperature is important. Oxygen availability ties into that, which I'll mention in just a little bit. Water movement is also important, also tying into oxygen availability. Let's go ahead and start with temperature. I want to talk about oxygen in the water. If you remember from the last chapter, oxygen exists in the water as O2. It's the same form that you breathe in the air, but there's a lot less of it in the water that's available for organisms to use. So, what type of environment produces more O2 availability? Colder equals more available oxygen, and moving water or flowing water tends to provide greater access to dissolved oxygen in the water. Why the heck does that matter? Well, here are 2 species to illustrate the importance of conditions in streams and rivers to their presence there. Let's start with the bottom one. This is a salamander called a hellbender. It's an absolutely fascinating species. They can get pretty large, like over 2 feet in length when they're fully grown. And if you look at them, they look very strange. They're kind of flat in appearance. They have a lot of wrinkles in their skin, right? A lot of folds in their skin. So, where do you find hellbenders? You find them in streams, first or second order streams usually. The water needs to have typically a steady current. Temperature has to be relatively cool. Why? Well, one thing to note is that the hellbender is the biggest salamander in the US, and the salamanders outside the US that get bigger than this are the Chinese and Japanese giant salamanders, and they live in very similar environments. So huge salamanders, and those ones, the Chinese and Japanese salamanders, they get to like 3 or 4 feet long or more. They're just massive. So why do these salamanders need flowing water, cold water? Because they get a large amount of oxygen through their skin. They absorb dissolved oxygen through their skin. Their skin is folded to increase the amount of surface area to get that oxygen. The water has to be colder, or at least cool in temperature, for them to maximize the amount of available oxygen to get. And the water that's flowing over their skin, that also increases the effectiveness of dissolved oxygen absorption. And so having cool waters with a large amount of water movement leads to maximum oxygen availability, in addition to the hellbender having the folds in the skin for more surface area, very thin skin to allow greater absorption of O2. It's perfectly suited for those cold, fast-flowing streams. Unfortunately, we've tended to affect those streams in very negative ways. We've reduced flow, we've increased algae growth in some of these streams, which has reduced oxygen availability, and these guys have had their population quite drastically reduced. St. Louis Zoo, though, is breeding them and helping to preserve the species, which is awesome. Lakes. So I should probably talk about the other creature in this picture. This is a bullhead. You probably recognize it's a catfish relative. They're in the same family. Bullheads are extremely tolerant of low oxygen amounts in water. And so if you have a farm pond with almost no water movement, totally stagnant, it gets really hot, there's a ton of algae growth in that pond, and so there's very little oxygen availability at all. You'll probably still have bullheads because they can tolerate very low amounts of oxygen. In stark contrast to what our hellbender requires, these guys tolerate very different environmental conditions. In fact, you're more likely to find the bullhead in a pond or a lake than you are in a stream. What is a lake? We usually use the word to mean something bigger than a pond, but technically a lake is just a topographic depression that collects water. So even the little farm ponds that you find dotted around the Ozarks here, those are all technically lakes. It's not just things like Lake of the Ozarks or big reservoirs that we consider as lakes. It's any topographic area that collects water. Lakes don't have a lot of movement of water. Some lakes will have streams that provide incoming flow or streams that have exit flow, but many lakes are lacking in water movement. In many ways, though, they parallel the oceans. They're like little mini ocean ecosystems. They have not an intertidal zone, but what's called a littoral zone. That's where you have cattails and sedges and other emergent vegetation that tends to grow. And in Missouri, most of our lakes are man-made. We put up a dam and then the water level rose and now we have a lake. I grew up in Minnesota where they have lakes that were formed during the Ice Age from retreating glaciers, and so there's like 10,000 plus of them up there naturally occurring. And so what we have here in Missouri, the lakes we have here, most of them didn't exist until the last 100, 150 years, and we created them. So they're kind of an artificial lake environment. But we do have ponds. We have a lot of small ponds, especially especially around the Ozarks. There are some very interesting pond environments, some of them related to certain springs and stuff. It's fun stuff to explore, but let's go ahead and talk about lakes a little bit more. Most lakes are freshwater. Like I said, the Great Salt Lake is one example of an inland lake that is not freshwater. Saline means that it has a noticeable amount of salt, so greater than 0.5 parts per thousand. In terms of what influences biota in lakes, just like with our stream, oxygen availability is considered the most important factor when it comes to what organisms can actually live there. And there are two major classifications for lakes, eutrophic and oligotrophic. I want to start by talking about what's called eutrophication. So if you've got a lake here, right, there's our beautiful lake right there. And we've got farm fields over here. And fertilizer is put with the crops. Fertilizer contains nitrogen and phosphorus. Rains will ultimately bring some of this into our body of water, which stimulates massive growths of algae and other vegetation as well. When that vegetation dies, bacteria break it down and they consume a lot of oxygen. And so using fertilizer, which runs into ponds and bodies of water, we're ultimately making things more what's called eutrophic. Eutrophic lakes, that's most of our ponds in Missouri would fall in this category, have low levels of oxygen and high levels of nutrient-stimulated growth. So you have algae, duckweed, etc. And like I said, they don't actually use up the oxygen. It's when they die, bacteria breaking them down use up the oxygen. So there's a lot less oxygen available for fish, but you do have high levels of plant and algae growth. The alternate type of lake is the oligotrophic lake. This is what the Great Lakes are, specifically Lake Superior, which I grew up 2 hours from, went there all the time. It's cold, it's deep, there's not a lot of plant growth in it, which means the oxygen levels there are very, very high. Nutrient levels are very low, and so plant growth tends to be pretty minimal compared to our eutrophic lakes. Very different set of species that you find here. Species you might be familiar with in eutrophic lakes here in Missouri would be sunfish like bluegills and long-eared sunfish. Largemouth bass also live in these environments. I don't think you get northern pike down here, but those type of things. In the oligotrophic lakes, you tend to have trout, salmon, fish of that nature. These are two, they're not, I don't want to say extremes, but they're opposite ends of the spectrum. And so you have lakes, especially where I grew up in Minnesota, most of the lakes around us were somewhere in between these. The term mesotrophic is used often, it means middle. So you have lakes that occur between these extremes, but eutrophic, low oxygen, lots of plant growth, lots of algae growth. Oligotrophic, high amounts of oxygen, not a lot of nutrient stimulating plant growth. So